Today I want to talk about a theorem that's really simple, but a little more versatile and cool than you might otherwise expect. It's a Sentry Theorem, and it states that the sum of the exterior angles of a polygon is 360 degrees. I mean, you might be more familiar with the sum of the interior angles of the polygon that follows this nice formula, n minus 2 times 180, where n is the number of sides, but the Sentry Theorem offers a really elegant proof of this fact. Just consider if every angle was 180 degrees and find the difference between having n straight angles and a polygon with n angles. The idea is that if every angle is 180 degrees, you just go in a straight line and your orientation never changes. However, if you follow along the edges of a polygon around until you get back to the starting point, again, your location doesn't change, but your orientation kind of does. While you may face the same direction, you've effectively done a 360 degree spin, and zooming out, that's exactly what it looks like. This is the 360 degree sum of exterior angles. It works for triangles, squares, pentagons, and it doesn't change regardless of the number of sides. And if you add this to the interior angle sum, you get the elegant 180 times n degree total, the equivalent of n straight lines. This is where most people stop with the Sentry Theorem. They decide it's a neat proof for the sum of the angles of a polygon, and most people simply remember that the sum of interior angles is n minus 2 times 180. But I don't think that does justice to the elegance of this theorem. Where the Sentry Theorem truly shines is when we have shapes that aren't simply polygons. Say a shape that might overlap itself like a star. I mean, sure, this star has 10 sides, and you can use your pretty little formula to find the sum of all 10 angles is 1440, and that the average angle is 144, but let's be real. Nobody cares about these stupid reflex angles. What really matters are the 5 outer angles, at which point most people start to calculate the angles of the inner pentagon, but that's actually unnecessary, and there's a far easier approach to this problem. Once again, we can imagine traversing the star. If we go along the designated path, to return back home, we can pause at the third point to notice that we already completed one rotation. Once we finish and come back to the start, we actually take two 360 degree spins instead of one. What this means is that the sum of the exterior angles isn't the 360 degrees it normally is for polygons, but it's 720. Alongside this, the sum of the interior and exterior angles is still 5 times 180 is 900 degrees, meaning that after subtracting the exterior 720, this leaves 180 degrees for the interior angles and an average of 36 degrees. That is elegant and simple. While this is an amazingly clean solution to an otherwise unassuming problem, I'll have to admit as always, the Sentry Theorem isn't all that powerful. Sadly, it is rightfully cast aside as you can always find another approach using just the interior angles. For example, you might have used the 108 degree angle of a regular pentagon in an isosceles triangle to get the 36 degree average. However, I still think the Sentry Theorem is cool and worth learning. There's something about it that is just so off-brand to conventional mathematics in that you have to somehow count how many times you will go around in your 360 degree spin. It's something that mathematics can seemingly so easily cut out of a problem when you go to group to add or multiply or exponentiate instead of count. But here, that visual counting offers a completely different outlook on the problem. If this were a problem with irregularities, you could get the exact same solution using the Sentry Theorem, while using interior angles creates dependencies in the details. And that subtle difference is one that captures two different worlds of math, specifics and generalizations, an ever-present challenge in all walks of life, not just math.